In this example, we use Python to compute and plot the partial sums of a series in order to estimate the sum of the corresponding infinite series. We wish to estimate the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n squared by using the first 20 partial sums of the series. We will also use Python to find the exact sum of this series. We begin by importing our SymPy package, defining n as a symbolic variable, adding the restriction that n must be positive and an integer, using positive equals true and integer equals true. And we define a to be an expression for the terms of the series. Negative 1 to the n plus 1, remember 2 asterisks give us the exponent, times or divided by n squared. Now, our process for computing the first 20 partial sums by hand is as follows. First, we want to substitute n equals 1 to 20 into the expression for a. And this will be done using the subs command in Python. Second, we will use the command cumulative sum to generate the list of partial sums. So we'll generate the list of partial sums using cumulative sum or cumsum command. Finally, step 3, we want to print and or plot the partial sums on the y-axis versus n on the x-axis. Now, to simplify step 1, we can use list comprehension to substitute everything into one command line. So we'll define a list of numbers from 1 to 20, which is easily done using the range command. Now, note that the command range a comma b creates a list of integers from a inclusive to b exclusive, much like the arange command you may have seen in a previous video. So we define n1 to 20 as range 1 comma 21. Now we use list comprehension and define the variable a1 to 20 as the list of numbers found by taking a and substituting n equals I for all values of I in that list, n 1 to 20. Since there are only 20 terms, we can print them to check our work as an intermediate step. When we do, we notice that Python gives us exact fractions. So if we want decimal approximations, we can, after substituting, add the evaluate floating point or evalth command to convert these numbers to floating point decimals. Now for step 2, the cumsum command is actually in the numerical Python package. It is not in the symbolic Python package. So if I go back to where I imported the SymPy package, I will import the numerical Python package with a shortcut abbreviation of NP. So I'm going to import the numerical Python package as NP. And so now we will define the variable s1 to 20 as np.cumsum, Because CumSum is in the numerical Python package, the NP tells Python which library it's located in. So np.cumSum, and we want the cumulative sum of the terms in the list from A1 to 20. If we print this list, S1 to 20 as well, we will see that if you compare the list for S with the list for A, all it is doing is just adding the terms of the list as we go. Hence the name, cumulative sum. So for step 3, we print the list, as we have just done, to see that indeed the terms are being added as we go. Now to plot the list of values, we want to plot these as points, so we use the numerical plot command found in the package matplotlib.pyplot. So after entering our matplotlib notebook command to tell Python to put the graph in the Jupyter notebook, we want to import matplotlib.pyplot as another shortcut notation, plt. And then we will do plt.plot. We want to plot n1 to 20 on the x-axis, s1 to 20 on the y-axis, indicating with the O in quotation marks option, telling Python to plot with points rather than connecting them. So both the list of numerical values and the graph give us an idea of what value, if any, the series is converging to. Looking at the numerical list, we seem to be approaching something a little more than 0.82, which appears to agree with the graph as well. In many cases, we can find the exact sum using the nsum command, which is located in the package mpmath. So we are going to import this command. Now, since there is no equivalent command in the SymPy package, we can just import the command itself rather than the entire package, as we've already done twice. So we are going to, from mpmath, we are going to import the nsum command and the command inf, which is how the nsum command recognizes infinity. Finally, nsum does not recognize symbolic expressions, so we cannot use what we defined earlier. So instead, we're going to create a function for our a sub n's using the lambda command. So if we put all this together, we're going to say that capital S is going to be the nsum of the function lambda, input n, output -1 to the n plus 1, divided by n squared. And we are summing that from n equals 1 to an infinity. And again, the nsum command uses inf for infinity. When we print the result, the sum of the series, we discover that the series converges to a number approximately equal to 0.822467.